Hello and welcome to our deep dive into fluid mechanics. Today, we aren't just looking at water moving through a pipe. We are looking at one of the most fundamental experiments in engineering history, the Reynolds experiment. If you ever wondered why smoke rises in a straight line before suddenly swirling into chaos, or why a garden hose flows smoothly at low pressure but sprays violently when you turn it up, you are observing the difference between laminar and turbulent flow. But how do we predict this change? In 1883, Osborne Reynolds, an innovator in fluid dynamics, answered this question. He didn't just observe the flow, he gave us a number, the Reynolds number, that engineers still use today to design everything from oil pipelines to airplane wings. By the end of this video, you will understand exactly how his experiment worked and the math that governs it. Now, let us look at how Reynolds visualized this battle. His setup was elegant in its simplicity, consisting of four main components. First, the supply tank. This is a large water tank containing a constant head system. It is crucial that the water level remains steady so the pressure doesn't fluctuate during the test. Second, the dye reservoir. A small container sits above the main tank filled with a colored liquid, usually potassium permanganate or a simple ink. Crucially, this dye must have the same specific weight, density, as the water so it doesn't sink or float, it simply flows. Third, the glass tube. A long, transparent tube runs horizontally from the tank. This is our stage, where the action happens. And finally, the regulating valve at the end of the tube. This is our accelerator. By turning this valve, we control the velocity of the water. As we open it, speed increases. Observation moon, high velocity. Finally, let us open the valve wide. The velocity is high. The dye filament completely breaks down. It doesn't even form a line anymore. It explodes into the water, mixing instantly in a chaotic, random motion. The orderly layers are gone. Inertia has won the battle. This is turbulent flow. let us run the experiment. We are going to slowly open that valve and watch the dye filament. Observation 1. Low velocity. We start with the valve barely open. The water moves slowly. Look at the dye. It forms a sharp, straight filament line right through the center of the tube. It looks like a solid wire. The layers of water are sliding over each other smoothly, like a deck of cards. This is laminar flow. The viscous forces are dominant here, keeping everything in line. Observation 2. Medium velocity. Now, let us crack the valve open a bit more. The velocity increases. Watch the dye line, it starts to waver. It is no longer straight, it is wiggling, creating a wavy pattern. The dye is starting to diffuse slightly into the surrounding water. We have entered the transitional zone. The inertia is starting to challenge the viscosity. We've seen the visuals, but engineers need numbers. We can just say it looks wavy. We calculate the Reynolds number for these specific velocities. Reynolds established specific ranges that apply to flow in a circular pipe. Kurava 2000, if your calculation results in a number less than 2000, you are in the laminar range. The flow is predictable and steady. Kudadal 4000, if the number is greater than 4000, you are in the turbulent range. The flow is chaotic and mixing aggressively. 2000 kurava kurava 4000, in this middle ground, we have transitional flow. It is unpredictable. The flow might switch back and forth between laminar and turbulent. Engineers usually try to avoid designing systems in this range because of that unpredictability. Ma'am, you do not redeem it. Ma'am, do not redeem it.
Everything changes.
So, why do we care? If you are designing a pipeline to transport oil, you generally want laminar flow because it has less friction, meaning you save money on pumping costs. However, if you are designing a chemical reactor or a mixer, you want turbulent flow. You want that chaotic mixing to ensure your chemicals react properly. Even in your own body, blood flow is typically laminar. If it becomes turbulent, it can be a sign of arterial blockage or other health issues. Osborne Reynolds gave us the tool to predict this behavior without having to build the pipe first. By simply plugging in our density, velocity, diameter, and viscosity, we can predict the future of the fluid. Thank you for watching this detailed breakdown of the Reynolds experiment. If you found this helpful, hit that subscribe button for more engineering deep dives.